Exercise 5.1 says for each of the following compounds, determine whether it exhibits a cis conformation or a trans configuration, or whether it is simply not stereoisomeric. So you'll notice all these have a double bond, and let's talk a little bit about what happens when you have a double bond. When you have all single bonds in a molecule, so say for example you have butane, those single bonds can rotate. So you could take that molecule and rotate this single bond here, rotate that around, and you could make that turn in to this molecule here. Oops. So these are really the same molecule. They're both butane. And you can rotate that bond there. You can rotate single bonds because they're sigma bonds. Remember, with sigma bonds, you get overlap of orbitals that's uninterrupted. So that overlap there has no interruption. So when you twist or turn those orbitals, the overlap stays the same. And so no matter how much the bond rotates, you still have that bond, and so the bonds can rotate without affecting the energy of the bond. If, however, you have a pi bond, so say you had 2-butene, that pi bond cannot rotate. That is not able to rotate like that. And the reason is, although the first bond that you form, the sigma bond, the first bond you form is a sigma bond, the second bond there, the pi bond, is formed by the overlap of two parallel p orbitals. So let me draw that here. This pi bond, that's formed, that second bond, every bond after the first bond you form is a pi bond. And you get a pi bond when you have two parallel p orbitals that overlap. So because they overlap, you get the bond, but you'll notice that in the case of pi bonds, the overlap is interrupted. And so the pi bond is always a weaker bond than the sigma bonds because the overlap is not as large. And also, in the case of a pi bond, the two p orbitals have to be parallel. If you try to rotate this bond, one of the p orbitals will stay going up and down, but as you rotate the bond, the other p orbital would be going in and out. They wouldn't overlap anymore, and so you destroy the pi bond. It takes energy to destroy those bonds. And so you're unable to rotate the bond because in order to do so, you'd have to destroy the pi bond. So there's an energy barrier to doing that. And so the big takeaway from this discussion is that you cannot rotate pi bonds. At least not without breaking them. You'd have to break the pi bonds in order to rotate the bond. So you can't rotate pi bonds, which means that this molecule on the left and this other molecule on the right, those are different molecules. On the top, because you could rotate that bond, the molecule on the left and the right were the same. But here, because you cannot rotate these molecules, those molecules are not the same. They are different. In the case of the molecule on the top, if you're trying to think about it more clearly, you could draw a dotted line down the long end of the double bond. And you could see that one group coming off of the double bond is going up, the other group coming off of the double bond is going down. Those are in opposite directions. That's different than in the other one, which, if you draw a dotted line going down the long end of the bond, one group coming off one side of the double bond is going down, the other group is going down. Those are on the same side. And so although you have the same number of atoms in both of these two molecules, and they're even connected in the same exact way, the molecules are oriented differently in space, and that makes them different. Two molecules that have the same number of and type of atoms and are connected in the same way, but are oriented differently in space, those are called stereoisomers. Iso means equal or same, mers means parts, so these are made of the same parts, but their three-dimensional arrangement, that's what the stereo is referring to, is different. Now, there's a term to describe each of these relationships. If the two groups coming off of the double bond are going in opposite directions, it's called the trans isomer. And if the two groups going off of the double bond are in the same direction, it's called the cis isomer. And you can remember it because the s in cis sounds like the s in same. So in this question, they're asking you, look, given each of these double bonds, is the double bond cis, trans, or maybe it's neither? So what we'll do is we'll take the double bond and we'll draw that dotted line down the long end. Now, we're going to look at each carbon in the double bond, one on the left, one on the right. And we need to see if the same group is coming off of both of those carbons. This only works if you have the same group coming off of both. So you have a methyl group, a CH3, coming off of that carbon on the right, and you also have a methyl group, a CH3, going off of the carbon on the left. So you have the same groups there, so you can think about cis and trans. And because one is going up and the other is going down, they're on opposite sides of that dotted line, and the stereoisomeric term to describe that is trans. So trans means they're going in opposite directions. So that's the trans stereoisomer, the trans configuration. Now if you look at this next one, this is an interesting one. If you draw the dotted line down the long end of the double bond, and you look at both of those carbons, you're looking for something that is the same that's on both carbons. The carbon on the right has two fluorines. So you have a fluorine and another fluorine. The carbon on the left has a sort of propyl group and a hydrogen, which is invisible, it's implied. So you'll notice that you don't have the same group on both of the carbons in the double bond. And because of that, this is not stereoisomeric. In other words, you don't have the cis and trans version for this molecule. Another way you could tell that you don't have the cis or trans version is because you have two of the same things attached to this carbon here. If that ever happens, it's also not stereoisomeric. So we go down to C. We'll follow our procedure, draw that dotted line down the long end of the double bond, and we're looking for something that's the same, that's attached to both of these two carbons in the double bond. Now, the carbon on the left is attached to a sort of tert-butyl group on the one hand, and the other thing it's attached to is an invisible hydrogen. The carbon on the right is attached to a sort of propyl group, but it's also attached to an invisible hydrogen. So because there's a hydrogen on each of those carbons in the double bond, this is stereoisomeric. And because the hydrogens are on opposite sides of that dotted line, one is sort of going up and the other is sort of going down, this is a trans isomer. So with D, we can follow that same procedure. We can draw a dotted line down the long end of that double bond. And we're looking for two things, the same sort of group coming off of both of the carbons in that double bond. So on the carbon on the right, we have this sort of isopropyl group coming off, and the other thing coming off of that carbon is an invisible implied hydrogen. On the carbon on the left, we have a sort of ethyl group coming off, and then we have an invisible implied hydrogen. And because those two hydrogens are on opposite sides of that dotted line, this again is the trans stereoisomer. Here we have tamoxifen. It's used in the treatment of breast cancer. So we'll draw that dotted line down the double bond. And we're looking for two groups that are the same, that are coming off of each of these two carbons in this double bond. So on the one hand, we have a sort of ethyl group. And then on the right, we've got this benzene ring. At the bottom, we have this big weird thing, this gigantic weird group. And on the bottom left, we have another benzene ring. Now notice, it's true that there is a benzene ring here, but it's not just a benzene ring. It's got all this other crazy stuff on it, unlike this one here. So those are different. So you have in blue two branches that are the same, the two benzene rings. Notice they're on opposite sides. They're on opposite sides of this dotted line. And so this is the trans stereoisomer. This is an interesting one. So draw a dotted line down the long end of the double bond. We're going to look at those two carbons in the double bond and look for branches that are the same that are coming off of those two carbons. So we have a few things. We have this cyclohexyl group going down, and then going up we have a butyl group. Oops, let's do this. A butyl group. Now on the other carbon, we have a butyl group going up and a butyl group going down. Now we saw this before. Although we do have the same group on both of the carbons, on this carbon on the right, it's both going cis and trans. It's the same branch attached to that carbon. Compare that with what happened with the fluorines a little earlier. You had a carbon that had two fluorines attached to it, the same group attached to it. Because you have two butyl groups attached to this same carbon, this is not going to be stereoisomeric. I mean, it would look like the butyl groups are both on the same side, so they're cis, but they're also on opposite sides, so they're trans. And what that means is that this doesn't come in two versions. There isn't a cis and a trans. There's just this one version of this molecule. It's not stereoisomeric. Here you have aconitic acid involved in metabolism. You can draw a dotted line down the long end of the bond there. We're going to look for two branches that are the same that are coming off of those two carbons. Now, on the left, we have a CH2 bonded to this group, which is called a carboxylic acid, and on the top, and then on the bottom, we have just the carboxylic acid. So the carbon double bonded to oxygen, single bonded to OH. If you go to the other carbon, we have that carboxylic acid again. So the carbon here is immediately bonded to a carbon that's double bonded to oxygen, single bonded to an OH. The other thing that that carbon is bonded to is an implied hydrogen. And so in this example, the two things that we have that are the same are those blue groups. Those are both on the same side of that dotted line. And so this double bond is in the cis conformation. So that's going to be cis-aconitic acid. So this is a taste of how you can start to think of how molecules are different when they're oriented differently in three-dimensional space. They may be all connected the same way. You may have the same number and type of atoms, but they're oriented differently in space, and that means that they will fit into different pockets and communicate different messages in living things. So one may be a medicine, while another is a cis version may be a medicine, while a trans version may be a poison, or may not work at all if it's a medicine. And so this is just recognizing that first type of stereoisomerism, that first type of things that have the same pieces connected in the same way but oriented differently in space, the example of cis and trans.